Assalamualaikum and good day. My name is Azin binti Saadan. My final year project title is Hemp Fibre Composites, Effect of Lamination Scheme on Mechanical Properties via Ansys Simulation, and my supervisor for the project is Associate Professor Dr. Aida Jumahat. The content of this presentation includes introduction, objectives, scope of work, methodology, findings, and conclusion. I will start with the introduction. Hemp is one of the most widely used natural fiber as reinforcement in polymeric composites. Natural fibers are the fibers that are derived from plants, animals, and minerals. Hemp fiber is classified as best fiber, which originated from plants called cannabis sativa. The advantages of hemp FRP composites include cost-effective, high strength, high stiffness, easy to process, recyclable, and low density. Natural fiber reinforced polymer composites are used in various applications, ranging from building and construction, car industry, aerospace, and sports due to its desirable properties. Ansys software is used as the main medium to conduct the testing needed to complete this project. Ansys software is also known as Ansys Mechanical or Ansys Multiphysics, which is a software made for general-purpose finite element analysis. There are three objectives in completing this research, which are to analyze the effects of layer sequence on tensile compression, flexural and quasi-static indentation, strength and deformation of hemp FRP composite, to study the effects of hole on tensile and compressive strength of hemp FRP composites, and to evaluate the effects of supporting ply angle 0 degree on the strength of unidirectional laminate of hemp FRP composites. The scope of work includes conducting literature review on previous studies related to natural FRP composite, hemp fiber, and the effect of fiber orientation on the mechanical properties of FRP composites. The second is to construct the model and simulation in Ansys software to analyze the performance of hemp FRP composites. The third is to compare the performance of hemp FRP composites with glass FRP composites for validation purposes. The methodology of this research includes Ansys simulation steps, elements created, and mechanical properties of the FRP composites. The Ansys simulation step starts with creating the model, followed by defining the element type, material properties, and failure criteria. Next, the section will be defined before setting the mesh of the model. Then the boundary conditions will be defined and the load will be computed onto the simulation. Only by then the simulation can be solved and the data can be recorded. For tensile tests, the dimension of the modeling is 190 mm width and 3.6 mm height of ASTM standard D5766, while for compression test, the dimension is 100 mm width and 3.6 mm height with ASTM standard D6484. In open hole tensile test, the dimension of the modeling is the same as the normal tensile test models with the hole diameter of 6 mm. The number of plies of the model for these three tests are 8 plies with total thickness of 2 mm, while the meshing size is 1 mm. In open hole compression test, the dimension of the modeling is the same as the normal compression test model with the hole diameter of 6 mm. The number of plies of the model are 8 plies with total thickness of 2 mm, while the meshing size is 1 mm. For flexural test, the modeling size is 60 mm width with 13 mm height, while the quasi-static indentation test, the dimension is 50 mm width and 50 mm height. The number of plies of the models for flexural and quasi-static indentation tests are 16 plies with total thickness of 4 mm and the meshing size is quadrilateral 8x8. These are the required data to be computed into Ansys, which is the material properties of glass FRP composite with volume fraction of 0.6 and 0.3, as well as hemp FRP composite with volume fraction of 0.3. The metric for the FRP composite is epoxy. There are two types of lamination scheme used in this research, which are with and without supporting ply angle 0 degree. The fiber ply orientation used are 0, 15, 30, 45, 60, 75 and 90 degree angle. This section is for the findings of this research, and I will share on the effect of lamination scheme of FRP composite, effect of fiber volume fraction and effect of hole on the FRP composite. Based on the graph for tensile test, the trend line of the curves were decreasing exponentially from fiber orientation 0 degree to 90 degree. Glass FRP composites of volume fraction 0.6 show the best performance, followed by glass FRP composite of volume fraction 0.3 and Hemp FRP composites. According to the maximum deformation contours, the type of deformation was elongation in the direction of the loading. Based on the strength reduction index table, glass FRP composite with volume fraction of 0.6 had the highest strength reduction index, followed by glass FRP composite with volume fraction of 0.3 and Hemp FRP composites. Lamination scheme without supporting ply angle 0 degree had higher strength reduction index, which means that the strength reduction of the lamination scheme with supporting ply angle 0 degree was more stable as the fiber orientation increases from 0 degree to 90 degree. Based on the graph for compression test, the trend line of the curves were decreasing exponentially from fiber orientation 0 degree to 90 degree. Glass FRP composites with volume fraction of 0.6 showed the best performance, followed by glass FRP composites of volume fraction 0.3 and Hemp FRP composites. Based on the maximum deformation contours, the type of deformation was shortening or compression in the direction of the loading. Based on the strength reduction index table, glass FRP composite with volume fraction 0.6 had the highest strength reduction index, followed by glass FRP composite with volume fraction of 0.3 and Hemp FRP composites. Lamination scheme with supporting ply angle 0 degree had lower strength reduction index due to the supporting ply angle 0 degree that improved the performance of the FRP composites. Based on the graph for flexural test, the trend line of the curve were decreasing exponentially from fiber orientation 0 degree to 90 degree. Glass FRP composites with volume fraction of 0.6 showed the best performance, followed by glass FRP composites with volume fraction of 0.3 and Hemp FRP composites. According to the maximum deformation contours, the type of deformation was bending in the direction of the loading. Based on the strength reduction index table, glass FRP composites with volume fraction of 0.3 had the highest strength reduction index, followed by Hemp FRP composite and glass FRP composite with volume fraction of 0.6. Meanwhile, lamination scheme without supporting ply angle 0 degree had higher strength reduction index. Based on the graphs, instead of exponential graph like the other tests, the result of quasi-static indentation tests were suitable to be plotted in polynomial graph due to the highest value of maximum quasi-static indentation stress, which were observed at fiber orientation 45 degree and the lowest at fiber orientation 0 degree or 90 degree. Glass FRP composites with volume fraction of 0.6 had better resistance to the loading compared to glass FRP composite with volume fraction of 0.3 and Hemp FRP composites. At fiber orientation 45 degree, the direction of the fiber caused the FRP composites to exhibit better shear-induced damage resistance compared to other orientation. The decreasing pattern when the fiber orientation increases from 45 degree to 90 degree was due to the similarity of the fiber direction of 0 degree to 45 degree because in quasi-static indentation tests, the FRP composites were clamped in on every side. According to the contours, the type of deformation experienced was indentation in the direction of the loading at the center of the composites. Generally, the lamination scheme with supporting ply angle 0 degree have better resistance towards deformation, thus having higher value of maximum stress compared to lamination scheme without supporting ply angle 0 degree. FRP composites with fiber orientation 0 degree had the best mechanical behavior. Thus, the FRP composite with supporting ply angle 0 degree had better performance compared to normal lamination scheme. The volume fraction of FRP composites play a significant role in determining the performance of the composite. The fiber volume fraction affects the strength of the FRP composites, as higher fiber volume fraction will strengthen the FRP composites in terms of ultimate tensile stress and Young modulus. Based on the figures, glass FRP composites of volume fraction 0.6 have higher maximum stress compared to glass FRP composites with volume fraction of 0.3 in all tests. It means that the FRP composites with higher fiber volume fraction had better resistance when subjected to loads. For open-hole tensile tests, the trend line of the curves were decreasing exponentially from fiber orientation 0 degree to 90 degree. Glass FRP composites with volume fraction of 0.6 showed the best performance, followed by glass FRP composites with volume fraction of 0.3 and Hemp FRP composites. The reduction of strength of Hemp FRP composites from fiber orientation 0 degree to 90 degree was lower compared to glass FRP composites. For open-hole compression tests, the trend line of the curve were decreasing exponentially from fiber orientation 0 degree to 90 degree. Glass FRP composites with volume fraction of 0.6 showed the best performance, followed by glass FRP composites with volume fraction of 0.3 and Hemp FRP composites. The reduction of strength of Hemp FRP composites from fiber orientation 0 degree to 90 degree was still lowered compared to glass FRP composites. Last but not least, I will conclude the findings of this research. According to the graph generated using the results, the value of maximum stress decreases as the fiber orientation increases from 0 degree to 90 degree for tensile compression and flexural tests. As for quasi-static indentation tests, the maximum stress was recorded at fiber orientation 45 degree. Lamination scheme with supporting ply angle 0 degree had better performance as it provided better resistance towards load, thus resulting in higher maximum stress and lower strength reduction index. Fiber volume fraction also affected the properties of FRP composites, as FRP composites with higher fiber volume fraction have higher maximum stress. The existence of hole in FRP composites lowered the maximum stress that the composite can withstand. To conclude, the mechanical properties of Hemp FRP composites can be comparable with glass FRP composites that have the same fiber volume fraction of 0.3. This is the end of my presentation, and you can contact me through the details given if you have any inquiries. Thank you.